In this video, we will be looking at shift operation exam questions. So let's just remind ourselves of the rules of shift operations. If we shift a binary number one place to the left, this is the equivalent of doubling the number. If we then perform another shift to the left, this will be the equivalent of multiplying the number by 4. So every time we do a shift, the number is doubling. When we perform a shift right once, this is the equivalent of halving the number. So if we shifted a binary number twice to the right, this will be the equivalent of halving the number and then halving it again, or taking a quarter of the number. So let's now look at some exam questions. Question number 1. Show the outcome of a right shift of 2 places on a binary integer with a value shown here. It is worth remembering that an integer is a whole number without a fractional part. So what I've done is I've wrote the number in the first line of this little table, exactly as the original number is in the exam question. And then I perform a one shift to the right. So every single digit moves down one place to the right. So you can see here, by following my cursor, you can see that each number has moved down one place to the right. Now that leads us to this final 0. When we move it down to the right, it doesn't fit in the table. So I've put a little strike through here just to represent that we're going to ignore that digit. So now we've performed a single right shift on the original number. But the question is asking us to do a 2-place shift. So we do the shift again. So each digit drops down one place, move to the right, move down 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 to the right, and then in this case this digit drops out of the table. So there are 2 digits that we will ignore because they have dropped out of the table. So our answer for a 2 shift right is this string of digits here. So I've wrote the number in here as the answer. If you wish to write it as an 8-bit number, then we will need to pad the first 2 zeros to ensure that we're using an 8-bit number. Question number 2. Show the outcome of a left shift of 2 places on the binary integer shown here. So again, I've wrote the original 8-bit number on the first row. Each digit is moved down and one place to the left, down and one place to the left, until we get to the final digit. So the 0 in red here has moved down and one place to the left. But that creates a space. So I've used blue ink here to represent this is an inserted 0. So now on this row here, we have performed a left shift operation once. The question is asking us to do a 2-place shift operation to the left, so we need to perform the operation again. Each digit is moved down one place to the left, down and one place to the left, until we get to the end where this blue 0 moved down to the left, creating a space, so we've had to insert yet another 0. Now, our answer is therefore this binary number here, or if you would like to use it as an 8-bit number, we are just stipulating the 8 digits from the rightmost least significant bit. Question number 3. Identify which shift operation will multiply a number by 4. Well, we know that the shift left multiplies the number by 2. It doubles a number for every shift operation that we perform. So therefore, if we wish to multiply the number by 4, we need to do a left shift twice. This will multiply the original number by 4. Question number 4. Describe a shift operation that will divide the number by 2 using this binary number given here. So we start by writing the original number in our table. Now we know that when we perform a single right shift operation, this will divide the number by 2. So using our table method, take each digit and move it down one space to the right. So the 1 must move down and out of the table, therefore we can ignore it. Each digit is then moved down and one place to the right. So let's just look at the operation of this right shift. The original number in binary is 101, which has the denary equivalent of 5. But the shifted number, the number 5 shifted to the right once, gives us the answer of 10 in binary, which is 2 in denary. Now we know the answer would be 2.5, but we are dealing with integers. Remember, an integer is a whole number. So when we're dealing with shift operations on an integer, we have to ignore the fractional part of the number. So in this case, this would give us an inaccurate answer. But for the limitations of binary shift operations on integers, we have to ignore the fractional part of the number. So in this case, we would be ignoring the 0.5. So the answer would be this number here. Or if you would like to write that as an 8-bit number, ensuring that we've got the leading 0 in the front to make 8 digits up.